Hello, RailsConf. How y'all doing? Great. So my name is Matheus. I work for a company called ThoughtBot. You might know us from our open source work or blog. If you use FactoryBot, that's us. We are on a conference about Rails, in fact, the last RailsConf. But way before Rails existed, in the middle of the 90s, a Japanese man has this divine revelation and created this language, and we call it Ruby. Without Ruby, there will be no Rails. So as a way to celebrate Rails history, we'll dive into Ruby today and understand its internal workings and how it affects our lives. There'll be a fair amount of code in these slides. Don't worry about it. I'll share the slides later if you need to. Just think about the big picture. Before we start looking at how Ruby understands our code, let's think about how we process text. Take this sentence as an example. When I see this sentence, my brain kind of divides it into different tokens. And for example, when I see the token, like the colon here, I know that what comes after the colon is explaining what's before the colon. Or when I see the apostrophe S here, I know that the thing after that belongs to the thing before that. So my brain separates a list of tokens, and we kind of get the relationships between those tokens as well. And after this process, which is very fast in our brains, we try to understand the meaning of it, if there is any meaning. Because not everything that's parsable has a meaning. So this sentence, as an example, I don't know what it means. And with Ruby, it's the same thing. Ruby reads our code, it splits it into a list of tokens, then it builds a structure with the relationships between those tokens. And again, not everything that's parsable makes sense. So for example, in this example, the definition is correct and the call is correct grammar-wise, but it doesn't have a meaning in runtime. So to understand all of this more deeply, we'll create an interpreter here right now. It's a very simple one, but it does everything that a normal interpreter would do. So I'll start presenting the language, and the language is very simple for now, but it will get increasingly more complex. At this point, our programs are just numbers. And by number, I mean a character from 0 to 9. That's the only thing that our language extends. So let's start lexing, which means also called tokenizing. Tokenizing is taking the code and outputting the list of tokens. So because the language is so simple, the tokenizer here will be very simple too. All we do is we use a regex to get all the words and numbers and special characters like plus sign, minus sign from the string. And we'll also create this language module, which is the entry point for our language. So whenever we want to run our language, we'll call language.call with the code. For now, all we do is tokenize it. So again, the tokenizer gets some code and outputs a list of tokens out. Even though we have the tokens out, we are not ready to parse to understand its information yet. So take this expression as an example. Because of math, we know that we have to do the left subtraction first and then the addition. Because if we did it the reverse way, we would get a different result. So the order of operations matter, and we need some kind of structure that tells us the order of operations. And that is called parsing. So parsing, the parser is similar to our tokenizer, but it receives tokens instead of the raw string, and it does some work. And again, this is the language that we are working with, and we'll try to make our parser code look exactly like the grammar. So we have the call method, and it has a program method, and the program is a number. And inside this number method, we'll parse a number. So first thing we do is we advance to get a token, and by advance, I just mean grabbing the first token from the list. And then we check. If it's nil, then we'll raise an error because our language requires a token, a number. Then we check. If it doesn't match the regex for a digit, then it's not a digit, so we raise an error again. All we care is number. But if it indeed is a number, then we will return a node, which in this case is just a hash with a type number, and the value is that token converted to an integer. So that's it. In 10 lines of code, we made a significant design decision for our language. All numbers are integers. If we had, for example, division, it would be division for integer numbers. Okay, so we add our parser now to our language module, and let's make this language a little more complex by adding addition. So the grammar is now like this. A program is a term, and a term is either a number, like we had before, or a number, a plus sign, and another number, or maybe a number, a plus sign, another number, a plus sign, another number, and you know where this is going. So because we can have multiple infinite-sized addition, we can write the grammar like this. A term is either a number and optionally any number of plus signs and other numbers. So we'll reflect the grammar in the code. So now program calls term, and inside term, we try to parse a number like we did before with the number method. Then we check, does the next token matches a plus sign? If it doesn't match, it's just a number, we return it. But if it matches a plus sign, then we'll try to parse an addition here. So we advance again, and that will return the operator, which is the plus sign in this case. And then we try to parse a second number. And now, instead of returning a single number node, we return a node of the type binary. And the binary node has the operator, which is the plus sign, and on the left side, the first number, and on the right side, what would be the second number. We could make this language more complex by adding subtraction as well. And to support it, it's pretty simple. Now we just look for a plus sign or a minus sign. So to understand this more deeply, let's walk step by step on how we tokenize and parse this language, this expression. So everything starts on the language module, we receive the code, and we call tokenize. With that string, it will return for us the tokens. And then we parse that. So inside parser, we initialize the tokens with a list of tokens that we received. We call program, then term, and inside term, we call number. And now inside number, we advance to get a token. So we got a token. It's not nil. It is matching the regex for a digit. So we'll return now a node of type of number with that value converted to an integer. So there you go, we get the first expression. Now we check, does the next token match a plus sign or a minus sign? Yes. So we enter the while loop, we advance, we get the operator, in this case the operator plus, and then we try to parse a second number, and we run the code again, but now we receive the number 2. And we'll return now the node binary. And we'll just replace the values here. The operator is plus, first expression is the number 1, and the second expression is the number 2. And that's it. We just built that tree, that structure that I mentioned that had the order of operations. We call this an abstract syntax tree, also called AST for short. But how do we execute it? How do we run this language? Well, we add another step to our language. We tokenize the code, then we parse it. Now we're gonna interpret it. And to interpret the AST, we receive it, the node, and we check its type. If it's a number, then we just return its value. But if it's a binary node, then what we do is we interpret the left side recursively. So that gets us the left side, and then we interpret the right expression. And lastly, we'll do the send call using the left side and passing as arguments the operator and the right side. And that's it. We did it. We just built a very simple interpreter. But again, let's walk step by step of how this is interpreted. So using that binary node that we received from parsing, let's walk step by step here. We check the node type. Is it a number? No, it's a binary expression. So we go to the binary expression branch. And then now we try to interpret the left side. So this will call the function recursively. So we are now interpreting the left side. We check its type. It's a number now, so we'll return its value, in this case 1. So on the left side, we have 1. Now we interpret the right side, and it's the same thing, and we'll get 2 back. And now we do that send expression. So this is basically 1.send plus with 2. Because addition is a method in Ruby, we can use send to call it. And if you do it, your language will return 3. And you might be thinking at this point, is that really it? It seems too simple to be true. But that's actually how Ruby worked until the version 1.8. So over 10 years of Ruby, it worked exactly like that. And to show you, let's see how Ruby used to interpret the number 42, only that. And that will be some code. Now it's C, so I don't know if you saw C code before, it's fine. So Ruby had this RB eval function. It received a node. And the first thing it does is defining this label. Labels in C are like checkpoints in the code. We'll see how this works later. First thing we do is we check the node type here. So there's this big switch statement with several cases. And for the number 42, we fall into the node lit case. And node lit here is similar to our number type. So we get the result from the nd lit attribute. And we break, basically return from the switch case. And that's it. It's not too different from what we did before with the case statement and the number node and the value. So let's try something a little more complex. Let's try this AND expression. So again, we are inside the RB eval function. We switch on the node type. There's a bunch of cases, but eventually we hit the node AND. And first thing, after entering the branch, we eval the nd first attribute that's similar to our left attribute on a hash. So this called the function recursively interprets the left side. Then Ruby checks if the left side is either nil or false, then break, stop executing. But if it's truthy, then grab the right side, the nd second here, and go to again. Remember that label that I talked about? Well, in C, the label, when you use go to, you basically makes the code start executing where you pointed at. So the code will go back to the again label and starts switching on the node type again, but now we are interpreting the right side. So this is why in a language like Ruby, even though you have something on the right side that would be an error, like summing a number and a string, because the left side is falsy, we don't even execute that. So there's no error happening here. And now you know how this is implemented. What's good about this interpreter is that it's very easy to build one. That's why Matt chose this architecture. But what's bad about it is that it's super slow. And it's slow because of how we represent this data. If you've been to the caching talk before this one, you probably know why. CPUs like sequential data. And when we store our data in that hash, that tree, our data is all spread out in memory, and that really hurts performance. To give you an example, to access the L1 cache in our CPU should take about 1 nanosecond. For the L2 cache, it's about 4 nanoseconds. And to access the RAN, which is where our data lives, it's over 100 nanoseconds. So it's pretty slow. So that's why in Ruby 1.9, after 14 years of this first architecture, Ruby changed. And it changed its interpreter to a compiler. And now the compiler receives the AST and compiles it into bytecode, which are a list of instructions. And those instructions are run by a VM. And this made Ruby 2 to 4 times faster on average. So instead of a tree like this, we need a data structure that is more sequential, where the data is packed sequentially, and that is a lot easier for CPUs to run. So we need to flatten that tree. And to do that, it's fairly simple. We'll walk this tree. Starting at the root, we first evaluate the left branch, and we'll generate an instruction for that. Then we'll go to the right branch and generate another instruction for that. And lastly, for the root node, we generate an instruction. And that's how we'll go from a tree to an array. So instead of interpreting the code right away, now we'll compile it, and to compile, we'll create a compiler. Don't worry. Oh, compilers are scary, but this one is very simple. We'll receive the AST from the parsing phase, and we'll return instructions, an array of instructions. And to create those instructions, again, we'll check the AST type, and for a number, for example, we generate a put object instruction with the value of that number node. But if it's a binary node, you might guess it, we'll call this function recursively on the left side, generate instructions for the left side. Then we generate instructions for the right side. And lastly, we'll generate this send instruction with the operator. And that will give us an array like this. But how do we run this now? Like I said, we'll use a virtual machine. And like Ruby, we'll use a stack-based virtual machine. So after compiling the code, we'll run it, and we'll call this VM. So the VM receives the instructions, and like I said, it's a stack-based VM, so we initialize a stack. Ruby doesn't have a stack data structure, but we can use just an array. We do some work with the instructions, and the last step would be popping the last value from the stack, returning that. Let's check the middle bit. So for each instruction, we check in a case expression. And if it's a put object instruction, we push that value onto the stack. But if it's a send instruction, we'll do something different. We pop a value from the stack that will be on the right side. Then we pop a second value from the stack, that's the left side. Then we do that send operation that we had before again, but now we push that value back onto the stack. So once more, let's walk step by step with a real example. So this are the instructions for 1 plus 2. So we check the instruction type. The first instruction is put object 1, and then we push its value onto the stack. So the stack now contains the number 1. Second instruction is put object with 2. Again, we check its type, grab its value, its put object, and we push the value onto the stack. So now the stack contains 1 and 2. Third and last instruction is the send instruction. So we check its branch as the send branch. We get the operator. We pop a value from the stack. So we get the number 2 on the variable right. We pop a second value from the stack. That's the left side. And we calculate the result using the send method. And we got 3 back. And we pushed 3 back onto the stack. So the stack now contains the number 3. And like I said before, we pop the last value from the stack as the last step. And if you do that, it will pop 3, and our language still returns 3. What's cool about Ruby is that you can see these instructions for yourself. If you call Ruby with some code and the -- dump instruction option, you will get this. If I clean it up a little bit and zoom in, you get this. These are the instructions for 10.up to 20. First instruction is put object with 10, then put object with 20. Then we have this opt send without block with the up to argument. And lastly, it leaves, which basically returns. So in a nutshell, that's how Ruby works since 1.9, until we introduce JIT compilers. And at this point, there's a lot of them. There's 4 JIT compilers at this point in Ruby histories. So it's similar to what we had before. So instead of just having a compiler that compiles the AST into bytecode, now we have a second compiler that compiles the bytecode into machine code. So instead of this compiler that we created, we also have a compiler for assembly, which is kind of like this. And I know what you might be thinking at this point. Yeah, this is cool and all, but I'm a Rails dev. I'm not writing a compiler. Why should I care about parsers? And one, because it's fun, but parsers aren't just for compilers. If you use Rails, and I assume you do, or IRB, or Robocop, standard, if you use the VS Code extension for Ruby, or really any of these gems, you are using a parser. In fact, you are using several different parsers, and that difference affects us on our daily work. You know when Ruby adds a new syntax and then Robocop doesn't understand it right away, or your editor thinks it's a grammar error? It's because of this. Each tool has a different parser, so when Ruby adds new features, everyone has to catch up with the new thing. This is also true if you are using a different Ruby implementation like Truffle Ruby or JRuby. Everyone has to catch up to Ruby. That's why they created this new parser, you might have heard about it, Prism. The idea of Prism was to be a single parser that could handle it all. It's a parser that is using the Ruby LSP extension. And since last year, actually, it's the default parser for CRuby. So if you are using Ruby 3.4, you are using Prism. So now we have this one parser. It's using CRuby, but at this point it's already using JRuby, Truffle Ruby, Natalie, Opal, and several gems, because it can do C, it can do it in Ruby. It's very powerful. So maybe one day, instead of this fractured ecosystem, we'll just have one single parser. And whenever Ruby adds a new feature, everyone can benefit from that right away. Okay, but why should I care about a VM then? Well, take this example. These are the instructions for the expression 2.send plus and 3, like 2 plus 3. And these are the instructions for 0 plus 1. Can we spot the difference? The first instructions, the first expression has more instructions, and the instructions all have arguments, while the second instruction, for example, we don't use pure object for 0 and 1. We have this put object int to fix 0, int to fix 1. These are instructions specifically designed to put 1 and 0 on the stack. Instead of using send, Ruby uses the opt plus instructions. And Ruby does that because we deal with zeros and ones and summing numbers. Those are very common operations. So it has optimized instructions just for that. It's called a fast path optimization. And we'll do the same thing to our VM to understand how it works. So in our compiler, specifically in the binary branch, we used to have this. Now let's say we want to make addition faster for some reason. So we check if the operation is an addition and we have a number on the left side and a number on the right side, then instead of doing what we did before, we'll do this. We add the put object instruction, but we'll sum the values right away in the compiler and put that onto the stack. So in a way, we are interpreting inside the compiler now. But if it's not an addition of numbers, we'll do what we did before. And if you benchmark this, you'll see that now addition is 20% faster than subtraction. What I'm trying to say here is that how you write code matters. There's difference between using method missing or define method. There's a difference between while true and using loop. And because of object shapes, there's a penalty if you use too much memorization in your code. What I'm saying is, I'm not saying that you don't have to use those features. You can write whatever you want, but know the trade-offs that you are choosing. And understanding the Ruby VM helps you to make those decisions. I guess no one would ask who cares about JIT just because why JIT? Why JIT makes your Rails code 10 to 30% faster and you don't have to do anything. So yeah, it's very welcoming. It's even enabled in Rails by default at this point. But what I like about YJIT is that its impact is much more than just performance. So Shopify did this benchmark where they benchmark parsing GraphQL queries in Ruby. So they compare pure Ruby with C extension, with pure Ruby with YJIT, all the variations that you could have. And what they found out was that writing pure Ruby with YJIT was faster than a C extension with YJIT. So in a way, Ruby is faster than C. And we started seeing PRs like this, where they rewrote parts of Ruby from C to Ruby. So we used to have this method for int.times, and it got replaced with this, which is not only as fast and much smaller, but a lot closer to the kind of work that we do on a day-to-day basis. Or this other example, which is more recent. They rewrote path name mostly in Ruby, and not only it was twice as fast, but it was a third of the code. So I believe that the future is more Ruby, because Ruby is easier. It's easier to read, it's easier to understand, it's easier to write, and I believe that it will be easier to contribute to, because it will be written in Ruby, a language that we use every day. So while Ruby is easy, but at the same time, I hope you notice that it's complex too. Has a parser, has a compiler, several compilers at this point. So to put it into Matt's words, the Ruby creator, Ruby is simple in appearance, but very complex in the inside, just like the human body. So to give you an example of this complexity, the Prism compiler has 8,000 lines of C code. The Prism parser has 16,000 lines of C. YJIT itself has 25,000 lines, and this is what the last time I checked months ago. And if you count all files inside the Ruby repository, you have over 1.5 million lines of code. That's the work of all these individuals, almost 400 people. And I just wanted to take a moment here for all of us to thank the contributors of Ruby. So give it up for their contributors. Yeah, they work really hard to make our lives easier. So to answer again this question, why should you care about all of this? Well, the most important thing is, as you go through your path in development, you eventually have to go beyond what you do now. You have to go into these technical, deep topics. Sometimes you have to read the gem source code because there are no documentation. You have to go beyond tutorials and blog posts and even official docs. You write your first gem, and maybe one day you have to debug a performance issue and you have to dump the C instructions. So I hope this talk is the first step in that journey for you. I hope it helps in unveiling the magic behind Ruby. And if you like this topic, you can take this further. There's this wonderful book called Crafting Interpreters. You will create 2 interpreters for the same language. The first one is just like we did initially, a tree walker, and then the second one is a VM. You create everything from scratch, no libraries, no nothing. So it's very fun. And if you want to play with the code that I showed you, it's all here in this repository. It's a GitHub repo, tbot.io/math-interpreter. And you can add something to our language. Do whatever you want with it. It's yours now. Yeah, and I hope this has helped you to see how Rails benefits from Ruby, how Ruby made Rails possible. And if it wasn't for Ruby, we wouldn't be here today. And that's what I had for today. Thank you, everyone. Do we have time for questions? One question. They asked, why do I wanted to learn about this? Well, I started messing with this during the pandemic, so I had some free time, and I found that book, Crafting Interpreters. You can read the whole book online for free. And once I started doing it, I just couldn't stop. It was fun to build my own language and to add whatever I wanted. Yeah, so that was it for me. That's it. Thank you, everyone.